So we've already talked about how reactions for GenChem 1, we've classified 5 different types of reactions, and we said that 4 of them fall under the idea of being oxidation reduction, and 1 of them is not. So why do we care about oxidation reduction reactions? It's because the electrons, as well as the atoms sometimes just the electrons, will actually leave and move through the reaction to something else completely. And I'm not talking about like within 2 atoms that are bonded, but I'm talking it will completely go to something else. So with that movement, we have the idea of, oh, you could put electrons in through like a wire or something. Maybe you can make the reaction go faster. With the electron movement, you can maybe capture the electrons and do something useful with the electricity they generate. Or if you're going to take organic chemistry, you can use electron movement to predict what a reaction is going to do. There's a whole series of rules, and you end up like deciding how electrons move through a reaction in organic chemistry that help you predict what's going to happen. So it's an important distinction to make sure that you realize that it is really important for something to be oxidation reduction reaction. So to figure out what you need to know for this course, GenChem 1, you just have to be able to identify something called oxidation numbers, and you have to be able to identify if something is undergoing oxidation reduction. You don't have to be able to predict what electrons are doing throughout the reaction, but you in GenChem 2, you will have to readdress this topic, and you will see what's going on with the electrons. And you will figure out things like what's the current that would be generated, and you can figure out how to balance a reaction that has a lot of electrons in it that are moving. So for now, we're just looking at oxidation numbers. So oxidation numbers, this is the charge in a compound, and it's the charge of an atom in a compound, and it would have if the atom was an ion. Now, this concept for ionic things is not new at all to you. You've done this before. You already know that lithium right here will give the chlorine its electron because lithium wants to be +1 and the chlorine wants to be -1. You already know it's going to do that. And the same for magnesium. You know that the magnesium in this compound wants to give the bromine it wants to give that bromine its electron, and that makes the bromines each become -1, and it forces the magnesium to be 2 minus, I should say. It's 1 minus in both those cases. I'll explain why in just a second. So we already know that's going to happen. So what we're actually talking about, though, is in a reaction. Now, these 2 things wouldn't react, and there's a reason coming up to explain why they won't react. But if they did, the question comes into play. So we're not worrying about the charge balance when we're talking about oxidation. We're worrying about where is an electron going to come from and where is it going to go to. So if these bromines, if we knew that one of these bromines wanted to give an electron up, like if they were kind of happy to do it, then we could say, okay, so if the electron's coming from that bromine, then we can choose, I'm just going to have to grab a new one because it's not going to let me do it. So if the electron's going to come from him, we go over to this side, well, which one's it going to want to go to? Well, it's not going to want to go to the chlorine because the chlorine's already filled up. It's going to want to go to the lithium because it's positive. So it's kind of based on not trying to balance the molecule's charge. It's not trying to, that compound, it's not trying to balance the charge. It's trying to figure out where will the electron move in the reaction itself. Now, as it turns out, though, when you're dealing with something that is ionic, what the electrons want to do make a lot of sense, and it just is based on the charges. So in the case of something ionic, we know that this has a charge of 1 plus. We know this has a charge of -1, 1 minus. This is 2 plus, and then this is 1 minus. Now, the oxidation number for this compound is going to be exactly the same. And the only thing is that for oxidation numbers, we'll put a plus in front, or a minus in front, or a plus in front, or a minus in front. But the oxidation number is going to be exactly the same because whether the lithium gets its, wants an electron back, and whether it gets from the chlorine or something else in the molecule, it doesn't matter. It's just going to be one that will accept an electron. So oxidation numbers for ionic things are really, really simple. Now, if you have something that's just sitting there as an ion in the solution, so like in water, when you dissolve things in water, you'll have like just K plus sitting there and just Br minus sitting there. Their oxidation numbers follow that same kind of an idea. The charge is 1 plus, 1 minus, 2 minus. The oxidation is going to be plus 1, 1 minus, and minus 2. And again, it's just because it's really clear that the electrons are on this atom right here. He's probably not going to want any, but he would be a good source for giving electrons up. And then if we're looking at neutrals, that means that it's an element that's kind of happy the way it is. So these guys have no charge at all. They're completely neutral. If you ever see something in a reaction, it's neutral. Its oxidation number is also neutral. So you've got some practice problems coming up. See how you do the practice problems before you move on and you look at covalent things, because that's where things start to feel a little bit less like something you've seen before.